So thank you very much everyone for staying until this time for my presentation. Yeah, before I thought I can move, so I need to really be focused here because usually I like to walk. So yeah, I'm systems engineer, and then I had this, I always say, as luck to work with Ludger and also Vera over the last 7 years. You can't hear me? Ah, it's very close and I can't see them. Okay. Anyway, I fix it. So originally I'm a systems engineer, and my talk also will be more at a technical level about machine learning, but also as a systems engineer I am also interested to find kind of abstract similarities in those seemingly similar things, dissimilar things. So as a systems engineer, you usually start fighting with disciplinary research, or how to play an interdisciplinary, or how sometimes you say how to play antidisciplinary sometimes also. So if you think about development of disciplinary research starting, let's say, from Descartes time, we had this setup that in principle we can analyze things part by part and objectively, and then we can add them all back. And then in principle this is the beginning of notion of domain expertise. So then in principle you have a kind of frame of disciplines, and then you become an expert playing in one of these cells. So in principle you learn what are the good questions, what are the main questions, and then you learn the answers. So this is the classical setup. So naturally you have this question that what happens in between, and this was the questions that started emerged to be asked like beginning of 1900 and from the field of systems engineering. And the idea was that is it possible to now think in a way orthogonal to disciplinary research? So this was in principle the vision of, I would say, systems theory started, let's say, 1920s, but as I will show you, in my opinion, it failed in 1980s because it was not abstract enough. But still, the story, I mean, the vision is interesting because you want to be orthogonal to what is happening, and then it's like kind of multiplicity of topics which are seemingly similar, but at the same time there is no way to talk in between. And you will see this in many, in principle, complex phenomena. For example, in cities, for example, you have this. In biological systems, you have this. So, but at the same time, if you look at these years from, let's say, from 1920s or 1950s till 1980s or also up to now, we have different concepts, and you see that maybe nowadays what we think about machine learning is a hype. You see that there have been a lot of hypes around, and then I don't know is it visible or not, because can I have a few minutes, because I think the resolution, I will change it if it's possible. It's not really. Is there any way to fix it, or I will continue like that? Because then I can't. Oh, okay, I found it. I couldn't find the search. So thank you, Doctor. So yeah, I hope it's working now. Yeah. Okay, great. Sorry for that. So, if, for example, if you look at these, just are keywords in the books that are, let's say, millions of books that you have. There's a project by Google called Google Ngram. They just counted how many times this keyword have been appeared in all of these books, I think millions of books. And then you see that these life cycles of what I call life and death of major concepts. And you can see that still they're living together, and then this is a common setup that you go to a lot of computational fields, and many times you see in an arbitrary way people take some of these ideas and then they're in a way pushing it. So my research is somehow on top of this, how we can find some meaning out of these patterns. So, and in principle, if you continue, you have these topics like system dynamics, cellular automata, agent-based models, in principle complexity theory, and then topics like metabolism that now you see these days in concepts like sustainability. These are, in principle, these are the ideas behind, but you see the starting time and also how they are evolving. So, in my opinion, if these are in a way, systemic concepts, you see that the vision was to be really orthogonal, but seemingly there are like kind of disciplines within systems engineering. And then I call this kind of traps of generic system models, because then as a systems engineer, you learn to use some of these ideas, and then you, in principle, you become a kind of nomadic person. You go to different disciplines and you say, okay, I think I know if you focus on system dynamics, you can find this kind of way of answering questions and so on. But I think this was the time, and also there were a lot of papers in 1980s that systems engineering principle is dead. And then in principle, I think the reason was it was not abstract enough. So, but what are the main concepts if you think about all of this concept that I told you? The main orientations are either around function or outputs of a system, or structure of the system, or the way you think about the processes, interaction between elements, and also context. And then you have different period of time of centralized or decentralized system, right? Decentralized approaches. And then you can see clearly these kind of approaches are everywhere. For example, differential equations or computational fluid dynamics, or for example, cellular automata or agent-based models. These are like different period of time from centralized models to decentralized models. And then also you have this kind of concept like network theory, which are focused on the structure of the network. And then we have a lot of them being celebrated. For example, space syntax is here, agent-based is here. And then later you have this kind of focus that maybe we cannot predict by these models, but maybe we can use them as a tool for learning. And this is when you are focused more on the context. And these are the shifts. I think this was the way I would say systems engineering survived. And from 1980s, and these methods like system dynamics or soft system methodology, which are like about tools for learning, not for predictions, they survive. But in principle, I think if you think about them as computational tools, they are a lot of fundamental limits. And it's very astonishingly because if as a systems engineer, if I look at many fields, I see the same concepts being used, but then there is no discussion. For example, you go to fields of energy modeling, you go to water flow modeling, you go to economics, they use agent-based, you go to transportation, they use it, but then there is no way to look why they are not working. And there are also people that are really thinking that if you have more computational power or if you have more data, we can do it. But essentially, this was in principle a main chapter of my PhD. Then I believe that either you have a valid representation, but then you have computational complexity, which is the case, for example, in the case of differential equations, and then you can decompose it in a way. Or in principle, these models are based on idealizations, or in principle, they are based on grammars and rules, or they are domain specific, and then they are limited in terms of integration. So maybe it's very funny, but there you have silos of researchers working with the same methodology, but they never talk. So for example, if you go to this field of integrated planning, then you say, okay, I'm interested in to know what is the heat effect, I don't know, in cities like urban heat island. And then in principle, you have, if you want to do it in a multidisciplinary way, you really focus, one group is working on building energy models, the other group building heat and energy, and then the other groups are working on transportations and heat emissions from cars and so on. And they're not really talking. First of all, they never do this kind of research, but if they want to push it also, they can't work. And then, for example, you have, in principle, a lot of problems with data because, for example, if you have a model of air pollution in cities and you're interested in predicting air pollution at the street level, if you use equation-based approaches like the case of computational fluid dynamics, you can't use all the source of the data. You know, for example, the style of living, the land use, also the way people walk and so on. These are all affecting air pollution. But then if you're interested in computational way of simulation, there is no way to integrate it because these equations are in principle fixed and then you need to just run it. So it's a kind of forward thinking about model. And if you think about it as a kind of over-parameterized approach, which is the case like in agent-based modeling, usually you have a fundamental problem, which is called the curse of dimensionality. And then in principle, these models become data hungry. And even with big data, it's not enough. So you can't validate these models. So It's, as I said, this is the case in the majority of computational disciplines, and I think one of the main problems I see, for example, not specifically in the case of design, but in, for example, if you go to urban planning or structural engineering, what I observe is that majority of people are just using these techniques because it looks sometimes cool, but then there are some fundamental limits behind it. And then my PhD was about how to try to find what are the foundational limits in this field of, for example, urban modeling. And in principle, the problem, I think, is in the concept of representation. And in all of these models, if you look, whether systemic or non-systemic, they're trying to represent the reality. And then if it's about water, you really want to mimic the movement of particles. If it's about transportation or land use planning, you really want to know, okay, if these, how many kinds of people we have, how they are walking, how they are, so you need to write the grammars, and you really want to be better than reality. And this is the problem, you can't be. So the limit is representation. This concept or this approach worked in many classical fields when you have less complexity. But if you are increasing the level of complexity, which is a function of the structure, function, process, and context in the system, for example, in a city, then maybe the idea of representing is in principle wrong. And it has nothing to do with the data or the approach, right? So, and also if I want to be a bit more aggressive, I would say complex systems is in principle as a self-contradictory topic, because with this definition of complex, it can't be a system. So this field also is a relatively active field of complexity theory, but usually this has this, it has this problem. So if I want to connect this to machine learning, I would like to formalize this in a very simple coding diagram. And in all of these cases, which are called representational, we think about coding as a kind of automation or mapping of knowledge that we have already. So coding or computation is secondary, and then automation automation is in principle the main role. And then in principle, if you think about it as a kind of logical diagram or logical setup, you need to know which types of data you need. And in principle, you need to know what are the logical relationship. This could be equation, this could be grammar, and so on. And then you produce the result. And then also you can validate it with the data. And here, the problem is that, as I said, you need to really represent it. And this is not working. So it's a kind of resistance and also fight between people that, yeah, you can do it one day if you have good computers and so on, but this is never ending. As an alternative to that, I think if you really think about the core of machine learning, which I would say emerged from 1950s, but I believe as I show you, it will be also, the historically is much longer, older than that. This is the main shift, that we move from representational approach to non-representational approach. So if it's this diagram is about knowing, in machine learning, and in principle, there's an, I think, article from Alan Turing in 1948. He talks about an unorganized machine. He depicts something like that, that what if we just, instead of thinking about coding as automation, we think about as this coding as a setup, which is learning. So do you have a learning machine? And in principle, this looks a bit messy in the beginning, and then you just focus backward. You just say, I want to see something. I really don't know what are the rules. I really don't know which kind of data is good for that, but I want to make this mechanism that learns by itself. So this is the core idea of machine learning, and it's not changing. I think still is the same, but then the changes or stages are based on how we are modifying this architecture or this setup. And the risky part, I think, is that, and that's the challenge, is that if this happens, in principle, these models will bypass all the domain expertise, because if expertise is about having answers for these types of questions in a certain domain, and here this machine learns that answers. So in principle, this would be a serious challenge. But nevertheless, it took 60 years or more to really get the data, because this setup of machine learning in principle is data hungry, or not data hungry, it is data demanding. And without data or without a coexistence with the data set, you can't make this machine learning. So you have these steps of computation that I wouldn't go to these details, but in principle you have mainframe computing, also then you have PCs and networks, and also then you have the so-called notion of ubiquitous computing, which is completely different. And then also we can talk a lot about what is big data and so on, but I will just show you like that if this was the case in satellite imagery in 1972, which is the first picture of the planet, now in 2018 we have this, and these are, in principle, you have kind of abundance of satellite imagery. And this was like also what Ludger was mentioning, that it's not anymore about one complete observation, or it's not about having the data, it's flooded. And in principle, if you look at this field that these days I'm looking, there are many companies, not just NASA or European Space Agencies, they're really asking whether you would like to use this data. And also, if you go to different layers, you have these sensors of local sensors, networks of sensors, and so on and so on. So data is not anymore a problem. And as a result of that, we had a lot of success stories in natural language processing and translation and computer vision. And then this created the hype, I would say, after 2010. So then, I'm not talking from the point of view of a computer scientist, but I'm looking from a point of view of non-computer scientist who is interested in computers, these fields. There are like 4 possible approaches which is happening. Either people deny this, or resist this, against this, or follow the hype, or embrace and learn. But I would prefer, in between these 4 categories, I would really like to, of course, to embrace and learn it. This is what we have been doing over the last 8 years. But also I respect those people who are resisting, because that's interesting, because then you can criticize what's happening and so on. And what is happening nowadays is majority follow the hypes, because big data is a hot topic. And then maybe there is something interesting, so you should go. But the problem with machine learning itself is that the moment you said, okay, I want to learn it, then how do you want to learn it? That's a big question, right? So whether you take another bachelor degree in computer science, which is not the case, or whether you follow the hypes again, what is the hot topic nowadays and so on, you do that, or you just try to learn it by experience, also try to also formalize it a bit, right? But if you go to machine learning, and also again, I am looking as a systems engineer to this machine learning field, the machine learning field itself is evolving like a swarm. So there are a lot of different methods coming every day. And for me, to be honest, it's a bit strange that you go to conferences and still you see that the people just take those methods which are published in 2018 because it looks good. And of course, you have this pressure from big companies like Google, Facebook, and so on, because they automate the whole process and then they advertise. And then people say, for example, these methods should be cool. But in principle, each of these dots in these swarms is like one PhD or many PhD students in computer science. And this is the way, and I really respect that, because this is the way the field is developing. And then, for example, maybe some of you know this field, this method which was developed in 2014 called generative adversarial networks, which is a very powerful concept. And then these are all the names of the revisions or modification of this. And even this is called GAN-Zoo, because each of them are, in principle, one is GAN and the others are some kind of modification. And then the question is that how we can navigate in this space. Are we completely reactive to this setup because you say, wow, look, this is cool, this is working, and I want to use it. And then if you want to resist, it's not working, but also if you want to learn, you are flooded. So you need to find a kind of abstraction. And another question is that, is it just a hype, or there is a major shift here? So the second part of my presentation will be about this shift. So now again, as a systems engineer by heart, my question is that, can we look at machine learning now as the original, as a possibility to achieve the original vision of systems theory, or not? So if you have again disciplines, is it something like universal between these disciplines that we can move? So then this is in principle my postdoc period from 2015 onward, and then I had these 2 main directions. First is, what are the main elements of machine learning in this space? and I was very curious to know all of them in principle. I don't want to just use any of them. I'm curious to learn. And also, I've been trying to collaborate with a lot of domain experts and also experts in different industry and so on. So I will not show this part about the applications, but I will just mainly talk about these elements from my point of view. So again, I go to this original picture, which is simple, because otherwise it's very easy to get lost in this cloud. Then if you look at this, this diagram, in principle we have very few elements. One is about function, or what always also Luther was mentioning in his talk, what is the question? So you don't care about the answers, but you look at the question. And then you are looking in a certain context for this kind of question. So in principle, this machine should have a measure for fitness or success, or also a measure for similarity, or in principle, when you are happy with the result of this machine. So this classically called least square method, which was developed in 1800, and also later, I mean, also based on works, I mean, there are some kind of discussions also based on works of Gauss. And then if you think about it, nowadays, I can also create a kind of catalog, but I wouldn't do it. It's called nowadays loss functions. And this is very important because the amount of the output that you get and depends on how you look at this output. This is the measure of fitness or success or similarity. You can create different types of loss functions, and for each of these different loss functions, you have completely different results. So, and a lot of people in this field, they just say machine learning is just about designing loss function. And if you design it properly, then everything is done. But then I don't think in a systemic way you should have other aspects. So the second part is the structure, or what is called in machine learning architecture of the neural architecture of this setup. And then in principle, the main and key contributions are all around this topic, how to deal with different notions of invariances. And invariance, for example, if you look at these simple cases, means, for example, when you have scale invariance, when you have rotation invariance, when you have time invariance, and so on and so on. There are different fixed types of invariances. And then you see the whole developments are around these notions, loss functions, invariance, and so on. And then majority of the methods you use for this structure is based on linear algebra. So now what is the modern way of thinking about this structure is called computational graph, which is a graph that you build, and this is the way I would say modern machine learning works. You just need to know what you want to get, and which kind of structure you want to build, and this is the computational graph, and it's computational, and this is already implemented in new platforms like Torch or TensorFlow and so on, if you're familiar with that. And then the second part is that if I have this architecture structure, if I have an output and I'm not happy with the output based on the loss functions, how can I change the system? So this is, I call the process. Classically, this is the optimization. And then the idea is that how I can move toward the part that next time I want to see what I want to see. So again, you look, I mean, the main concept now is backpropagation or evolutionary strategy, but also if you go back to calculus, you will see that the references are not that new, and everybody admits that, but now it's just possible to implement it in a proper way and in a kind of a structured way. So this is in principle optimization. It tells you if you have a structure, if you are not happy, what to do next time. So this is in principle the feedback. And then context means where and when you're talking about what. So in principle, this means in data and different modalities of the data. And then again, you can see that a lot of algorithms have been developed around these topics, how to handle different types of data. For example, you have homogeneous data or heterogeneous data set, or for example, you have Euclidean space or non-Euclidean space, or for example, you have graphs and this kind of stuff. So in my opinion, I could expand this as a kind of catalog, but I don't think it would be helpful. So I will focus on only computational graph. I will briefly tell you what are these elements. I mean, in principle, in linear regression, and from that, I will talk about 3 stages of machine learning. So as I said, in principle, you need to have, this is a case of linear regression, which is like very old method, right? In principle, you have this kind of points, and then you want to fit a line in this case because it's linear to this point, and then the way you measure the quality of this system is simply you just calculate the distances of each point to this line. So in principle, if each line is a dot, you have a space of potential dots. So if you start with random, every time you get some of the errors, and this is called least squares. And then in this case especially, you can find an absolute result, but also you can search based on this the setup I told you. And in principle, out of them, you can say this is the optimum given this loss function. If I change this, because this is the average error, if you want to say, no, I care about the maximum distance or the maximum regret and so on, then the loss function will change, and then you have every time different results. But based on this, I will follow the next based on what are the stages of machine learning, and I would say why we have a hype in principle about machine learning. So the focus is just computational graph. So if we look at this, I would say before 1980s, everything we have is kind of linear. So in principle, you have one central memory and one global prototype. So it's just one dot. Everything that you have is the capacity of one dot. And central memory means, for example, that this abstract point can generate complete instance of the object. For example, if it's about chairs, if it's about houses and so on, this is like an average house. This is just a generic house in this case, right? In the computational graph, you really build it like that. So these are the inputs. You have only one dot or one function. And then you say, what is the output? And then you put it in this loop, and then it works. And I would say from 1980s to 2010, you have, in principle, multiplicity of these dots. And in principle, the key issue now is that if I don't want to have one dot, how I can orchestrate them? Because with one, you just fit one line. And in a way, you can think about a kind of locally linear setup, or you can think about, for example, self-organizing maps, or many other methods. I don't want to go to techniques like random forest and so on, or even clustering. Then in principle, the whole algorithms are around this topic, how to orchestrate these abstract points. And the main problem is that technically and also theoretically, the capacity of these models grows linearly as the function of the number of points. Because what happens here in principle, you can think about them as like kind of clusters or whatever, but in principle, each of these dots becomes a new dimensionality for itself. And then if you say, I have a lot of data points, you want to say this data belongs to which of these classes. So if you want to have more classes, you just can add more, and then this capacity increases linearly. But then this is, I think, the reason for the main hypes these days, and I think this is when you change the whole story. And now you just say, instead of having one of these layers, what if I simply say, I will think about the output of the first layer of my computational graph as the input of another one, and also continue like that. So this technically didn't work for many years, but now it works because of the huge amount of data. But I think this is a major shift, and also conceptually, I will explain in a few minutes that why this is a major shift, that this is happening. And I will go, because of that, I need to mention a bit of mathematics of that. This is the diagram. For example, think about linear, when we talk about linear or even multilinear setup. If you think about Fourier transform, which was a method developed in late 19th century, in principle, you're playing in the space between time, not between either in time or frequency. And then because of that, each of these blocks are similar to one of these points. So these are like projection points. So when you do Fourier transformation, in principle, you move from time to frequency. And then if you repeat it 4 times, you go there, and then you go there. So you go in the same place. So by repeating that, you don't get better. But also you can think about it in a lot of other methods like PCA and so on. But this is another notion, because this is a kind of geometric way of thinking about this transformation. The other way is if you think about it in the vector space. Usually you have a data set, and you learn some of these detectors or prototypes or whatever you call it, and then you convert it to another space. And then you can do this back and forth movement, you can remove some of them and so on, they can be clusters and so on. But what is happening is that you can't escape this space. And in principle, these are linear transformations, or in the case of this diagram, translation. So what is happening here is that we are a bit scared of this space. We are all moving either here or we jump there. So the question is that, what happens here? What is this space? This is a meaningless space. And I think with all of these linear methods, you can't work in this space. And if you do that, all of your prototypes or center of the clusters look random. So usually that's not the case. These are all meaningful for you. You can see that they all correspond to different type of frequency, but here it looks random because you are in the middle of a space of time and frequency. And this is the reason why I think many of the methods have less capacity. And it's very interesting if you stack them together, just by giving up, because we just give up the meaning, you get astonishingly better results. Because this is the space that we never discovered. We always scared of this space in between because it's meaningless, and you always focus on one of them. So in a way, what I explained to you could be like that, that if you have this layer, I simply start with this movement in this random space, which are seemingly meaningless, and then I move step by step, and this is not anymore, you don't need to explain it in the space of time or frequency, but this is a vector space. And this is an area that you have a meaningful context. This is your data set. You know what you're talking about. This is the result. And then you go there, and we create kind of sequential transformation in this vector space. And then in the end, you land to the place that you want to be. And this area only is a meaningful setup, and here is completely meaningless. But by that, we have this capacity to work in this domain. And because of that, you're harvesting a lot of more capacity. And then this setup that I told you works very well, because if you land somewhere here and you want to be green and it's blue, you just say, okay, next time I should go back. So this whole process that I explained helps you to adjust these random vectors. And it's very funny because people try to say that these random vectors in the end become similar to this Fourier transformation, but I have done this for many cases, and it's very interesting. You get much better results, and the result is these filters are always random. So you can't make sense of it, and it's a wrong direction, but you should just accept it. This is a space, I would say, is a kind of quantum space, right? So I just want to conclude this part, and in principle, what is happening here is that we have 3 stages of machine learning. One is a linear regression, which is when you have 1 dot, or if you repeat these dots, you have manifold learning. And then in principle, when you have this, you have, if you say linear regression is addition, when you repeat it, repetition of addition is multiplications. And if you repeat multiplication, now you have a power function. And that's why the capacity of these models are increasing exponentially. Because the space in multiplication is small, but the space in exponential function is increasing. And if you add 1 layer, the capacity of these models increases combinatorial. But then you lose some important factors, actually. So another thing is that if you think about memory, or the way we think about data, in linear regression and also this manifold learning, we think about memory or storage point as a kind of either particle or wave. And then only here, you can't say where this pattern is happening, because it's in between. And at the same time, it's all of them and it's none of them. But here, for example, if you think about clusters, you always have one of these points get activated and you say this is one cluster, the other one is not activated. But here, all of them are playing together. So in principle, memory is embedded in this graph. And then in principle, memory is also at the same time particle and wave. So if this is the word of kings, or one king or one god, this is space, I think, I would call it political parties or brands. When you have clusters, you say either this group or the other group, and then of course you can build it up, right? But then the question is that here, everything, it becomes a bit again individual, because you really don't know. You can compare 1 to 1, but you lose the abstraction. And I think this is the current situation we have also in the society, because this setup gets complex, and then you can't trust anymore to these groups which are there. And then as an individual also you might feel very powerful, but then you lose the communication point. So one of the big maybe points would be, do we need new ways of discussion or communication in this setup? Because I think this is the way, this is how we are living now these days. And also Lutger mentioned this part. And then definitely there is a risk here to shortcut back to stage 1, not to stage 2, because you are bored with stage 2, and then you can easily go shortcut to something which you think it's solid. And this is, for example, a very dangerous move in society, but you see that this can happen, because here you lose the basis. And in principle, what I tried to show you here was the whole thing that, no, sorry. Here you are very interested in this orthogonality or basis, so you just say either time or frequency and they're orthogonal, they don't share and so on. But here you are in this space, so you lose the basis in a way. So you are in a way alone. So you have better results, but also you lose the connections, right? So then, just to conclude the discussion, because I could go further and I should be careful with the time. The concerns and possibilities, and I see this as two-sided setup. It could be concern, it could be possibility. First thing is, machine learning is good at finding answers. So this is a big alarm for domain experts. And I've been talking about this because I'm working with domain experts, and I say in principle, you are good in having answers to few questions, but now with machine learning, we just say we find the answers, but the question is important, right? So then these fields are in danger. In principle, those fields which are based on domain expertise. But at the same time, machine learning is not able to find good questions. I've never seen, I don't believe you can find a good machine learning method which generates something, for example. All of these applications are kind of analysis, some kind of discovery, but not generative. And also, as Lutger was mentioning before, we have this human intelligence, which is ability to find good questions. So, in a way, if we are humans, we know good questions, and if we learn this in a kind of literacy, then it's a big opportunity, because everyone is a superhuman, right? And this big data is available. So the first thing is that classical disciplines, I think, will need to redefine themselves. And another concern, again, related to the previous one, is that if you have this setup that now we have this exponentially growing capacity, if it's concentrated, this can be tyrannic in principle, and this is, for example, the case. And I think I will mention, again, I stress on this topic of private Google that Lutger is very interested, and I think it's a very interesting topic. So if you think about it in a negative way and in a helpless way, that you don't know what is this data, what is machine learning and so on, this looks very dangerous. And then you see this is the discussion in the society. But on the other side, if you start being literate in this field, and it's just, you don't know when you know how to speak German, for example, or English, for example, in my case, because I never learned German. And so you learn it, and then you see, you look at it differently. And so in that sense, in a positive way, with this literacy, it could be seen the whole power of big data, and also open data, and machine learning, and so on. This could be a new capacity to have human, super individuals, right? So, but I just want to stress this because I saw Lutger is doing that. I will put this part also to mention that now we have in principle two alternative pathways. One is that we have these big players, and then everyone becomes a user of one global map. Also, everyone could be a user of one generic search engine, or everyone could have one unique global map. Or everyone could have one unique search engine, because these aspects are different. So you can really make the whole planet, and I'm doing that because the data is available, and then you can make this, and everyone has one map, one whole map, the whole planet. And this is definitely different than this planetary urbanization, for example, approach, because then always they try to go back to the stage one because they want to say what's the picture. But here we just want to say everyone has its unique picture. But since you are literate, you learn how to talk to each other, but you have the whole planet. And that's what it interests me, because this is possible and I mean feasible also. So in that direction, for example, I started working with planetary data. And this case was, for example, I was interested to know, can we find, let's say, similar cities? And the question is that what is similar, right? So I said, okay, I care about road networks. Can I find road network? In this case, I have data from literally 1.1 million cities. You take images of them and then feed it to this setup, and then it finds similar road networks. So if you have, now you have a kind of visual query. You have one city, and then you see where else in the planet has similar city to mine. So imagine, I'm also pushing this in the kind of startup idea. Now we are thinking about finding a house. You have a house and you say, I like it, and I have certain interests. So then you go to the market. You have at the moment search engines which are generic, right? So what if I have the access to whole data? And then again I said, I lived here, I like these kind of things, even implicitly. Can you find similar one to me? And if you go to the next one, the next person is different. So in principle we have infinite, or in principle as the number of people, users, we have different types of interfaces, different types of search engine, right? So also, I will just show off this last part, that because it takes a lot of time to implement, I couldn't finish it, but in principle, I'm very interested in this open source map of the planet called OpenStreetMap. I think some of you know. And this is a kind of wiki-based map. So they started from 14 years ago, and now they have 4 million users, but majority of the updates are coming from a lot of interesting people that I'm not one of them, but they really spend time to update maps, and then it's like Wikipedia, and then they upload their data. And also in some cities they realize that using OpenStreetMap is cheaper than having like a proper website. So in OpenStreetMap you literally, over time, you get the whole planet. So this is the map of all the buildings in the planet, right? So now this is just rendering, but in principle you can get the data. So if you go to, for example, Vienna, so you have all of these buildings, like there are 300 million buildings, and out of them you have around 20 million of them with a lot of good information, like 3D extrude, and also who is architects and so on and so on. You have land use and so on. So this is a data set. At the moment it's not really fast. I couldn't make it faster to just search here. So in principle the idea is that also you have a lot of other layers. For example, let me show you something else. For example, if you are interested to know access to transportation, so data from transportation is there, you can calculate these kind of maps. But the question is that I don't want to celebrate transportation map, but I want to make this available for everyone. And since this is cheap to do it, you can say, I care about this, and then you will see this colored map. So everyone has a different colored map. And then also, for example, if you're interested to know, by the way, what is the most frequent point of interest in the planet, it's interesting, is a place of worship or different types of religion. So also you can qualify buildings based on different religions. For example, this is blue is Islam, I don't know what is yellow, and then this is green. So also I can qualify buildings like that, but this is just arbitrary. So you can do it with different things. Also, if you have better data sets, for example, in the case of USA, this is a recent data set. It's out of it's not OpenStreetMap. So also you can get this data, for example, with better quality. You can calculate the density. Also, you can go to each of these buildings. You have polygons. As I think Ludger was showing this properly, you literally open the whole planet is an XML file, and each building is an is a polygon. So you literally say, for example, I'm interested to know number of corners of the buildings all over the world. Is there some kind of correlation? I'm interested to know, for example, what is the size of the buildings, right? Footprint of the building. And then you see definitely there are some kind of a spatial correlation. But I'm not trying to show you, it should be fast, and it's really fast, so this is important. But I'm not trying to say that it's important to know what is the footprint of the building, but it's just one of the possible questions. And then if you add a lot of them, so in principle I can start asking questions. I say, if I'm in this building, is there any similar building based on these questions that I have in the world? And actually I'm doing this test for kind of real estate early stage development. And you have a site, and then you know what's going on around this site. And then the question is that, is there any similar building? And we don't know what we want to do. Can we get some ideas? So this method simply search in 20 million similar buildings, and then it says there are like 200 locations which might be interesting for you. So it's a kind of idea generation. Then you go there and you see what's going on, right? So yeah, you can do a lot with that. And I think I tried to here show you some cases, not to focus on the application, but to show you that these technologies have two sides. With literacy, you can really think about it as a new potential. And the opposite way, if we are passive users, we will be passive users. And I think that's a big risk for big companies, because also I don't think by complaining you can change this direction from, for example, this peak. So we need to really be active and learn and then appreciate these technologies in a positive way. So thank you very much.
And now we move over to questions and comments, please.
Oh, this will be a hard question.
Okay, since I developed the gnomonic Fourier model, it's quite interesting because there is a recent development. The thing is that the intermediate angle between this is not really meaningless. It is meaningless if you try to visualize it, and it looks random. Now, what it turns out, it is that this is the only way that the system can start accumulating memory. So the angle, the in-between, is the way to create memory. It's similar to how our brain recalls things. It looks random, the pictures we make of the past, but it's all about an angle in a plane, but the axes of this plane are of logarithmic nature, so they are not linear.
No, I agree with that.
Yeah. So just a comment, I think it's quite important not to say that it's meaningless and random, but it's the way that we have a system with a memory now.
Yep, that's right. Meaningless in terms of time or frequency, so always you can project it to either time, and then you have an amount of information which is equal at the end. But you're right, because literally what you learn is the angle, but the problem is that you know what is this 90-degree translation corresponding matrix, and this was the great work by Fourier, but for the other cases you don't know. But definitely if you can do that, I mean, if you can parameterize Fourier based on parameters, definitely this could be a great step. But what is happening here is that, I think what's happening is that in principle, you can think like that. Also, you can just say, because it's cheap, I even don't want to learn angle, right? Because I just say, I'm very opportunistic to learn all of these pixel values of these blocks, and then it works. So in that sense, I think that's what's happening here. It's not anymore about time or frequency. This is completely in a vector space. But I believe if someone, I think we discussed this many times, if we can formalize that to that setup, this would be really cool. I mean, it should be really interesting. But the current setup, I think, it's very opportunistic, because also it's a kind of machine learning in principle is not a scientific field, or it is a scientific field, but it's a kind of engineering, because most of these developments are based on tricks of engineers. So now what is happening here is that in a pragmatic way, it's working, it's enough. But then if someone is able to say, especially with this setup, and I think this is missing in the literature of deep learning, for example, if somebody is able to do that, instead of having a lot of redundant parameters, Because what's happening here is that if each of these pixel values are one parameters, and this setup should learn all of them, but literally you just say, I just need to learn the angle. And if I can learn the angle, then it's done. This would be a great step, and maybe you're right. I mean, I'm not sure the way I was thinking about meaning, but based on your explaining, yes, that's right. Thank you.
I have another short comment. The last example there with the globe. It's important to say that this is your private globe, huh?
Yes, yeah,
that you're
exactly.
able to, I didn't get it this explicitly. So it's
Yes.
a private globe and you are able to develop
Exactly.
this performance in 2018 in a few months with actual tools.
It's actually 10.
So it's
10,
not
yeah.
Google Earth or some big company and so on. You are able to do it as a single person in a few months and bring it to this performance and simply calculate the whole planet. This is possible. That's so amazing with that.
Yeah, exactly. Okay. Yeah, I can also show you, I mean, it's really simple. I mean, also Ludger was performing this. Literally, you can do it, and it's not just about, so we can start and doing it now, and then the whole thing that I showed you, it was like a few days. And then it's everywhere, because they're all, in a way, XML, as Ludger was talking. So you really don't need to learn data models anymore. So you just say, I am interested in this, and then you go to a certain context, you find the data, and then you can do it.
Yeah. You were saying, some part on your presentation, you place the political parties with the brands. Wouldn't you say rather that these global localities that individuals are able to articulate out of the plenty would be the brands?
I have a question mark here. I'm not sure about this part, but
you're
this
thinking about it, okay.
Yeah, I just don't know which one is correct. Yeah, but you think here there are brands or here?
Yeah.
Yeah.
I don't know. Yeah, I would say so. But it's just a question.
Thank you.
Are there more questions? Then I say thank you very much. Thank you very much for your attention.
Thank you very much.